Hello everyone. Today I will go over problems from section 5.4 in the topics of work. Because of the length of these sections, then I will break it up into two videos. The first part will cover the general case, and then the spring case, the cable with weight case, and then after this I will go over in the second part, so another video, I will go over problems that has the water pump. Okay, but let's do this one first. Keep in mind that the formula for work is force times distance traveled. But if the force varies with respect to the position, then the work will be integral from the initial position to terminal position of dx. Okay, now let's see number 2. Compute the work done in hoisting an 1100 pound grand piano. So let's say this is the piano, and then which is 1100 pounds, and then you need to raise it up to the third floor, which is 35 feet above the ground. So the work will be now notice that the weight is constant throughout this journey, 35 feet up, right? So the work will be simply 1100 pounds times 35 feet, pounds feet, or feet pound. Okay, just like that, because the force is constant throughout the traveling throughout when you go through that. Okay, number 4, a variable force. So this is actually the force function. Moves a particle along a straight path when it is x meter from the origin. So if this is x here, then the force associated to that is 4 square root of x. Now the question is, calculate the work done for moving the particle from 4 meters away from the origin to 16 meters away from the origin. Okay, so the work will be integral from 4 to 16 of 4 square root of x dx. Okay, because the force function varies with respect to the distance from the origin. Okay, now then, how much work needed to move this object or this particle from 4 meters to 16 meters away from the origin. Okay, so that's the setup. To integrate that, of course, I think you can just do it yourself, right? Okay, but I give you that setup. Number 10. Let me give save some space here. Okay, number 10. If the work required to stretch a spring 1 foot beyond its natural length is 12 feet-pound, that's the work, huh? So let's say this is the spring, okay, and this is the natural length. Let's call that 0. No, I call it x0. And then I need to extend it by 1 foot beyond that. So this is 1 foot. The work required is 12 feet-pound. Okay, so the work will be integral of kx dx from 0 to 1. That will be k over 2x squared from 0 to 1. That is k over 2. But this work is said to be 12. So from here we get k equals to 24. Okay? That's if we we stretch that by 1 foot, right? Okay, now, so from here we see that the force function is equals to 24x. And if we need to stretch that by 9 inches, remember 9 inches is 9 over 12 feet. Okay, that's 0.75 or 3/4 foot, right? Okay, so the work will be integral from 0 to 3/4 of 24x dx. This will be, let me just go on, this is 12x squared from 0 to 3/4. The work will be 12 times 9 over 16. I think I can cancel by 4. That's 3, that's 27 over 4 feet-pounds. Okay, that's for number 10. Number 12, if 6 joules of work is needed to stretch a spring from 10 centimeters to 12 centimeters, oh, this one is hard. So let's say we have that spring. We don't know what is the natural length. Let's call the natural length to be L. Okay, and then we need to stretch that from 10 centimeters to 12 centimeters. Let's say this is 10 centimeters and this is 12 centimeters. So from here to here. Now 10 centimeters is 0.1 meter and 12 centimeters is 0.12 meter. Okay, now then the work is integral from 0.1 to 0.12 kx dx, is it right? It says that this is actually 6 joule. Okay, so this is k over 2. Oh, I'm sorry. This is, I need to account for the natural length. So I need to subtract by L here. I almost forget that. I'm sorry. Okay, so this becomes k over 2x squared from 0.1 minus L to 0.12 minus L equals to 6. In other words, the work, which is 6, is equals to k over 2, 0.12 minus L being squared minus 0.1 minus L being squared. Let me simplify this a little bit. So this is 12 equals to k times 0.0144 minus 0.24 L plus L squared. That's for the first group. Minus the second group is 0.01 minus 0.2 L plus L squared. So 12 equals to k times 0.0044. I got it from here. this guy minus this guy. I get this guy. Okay, and then minus 0.04 L, which I get from this guy and this guy. And the L squared term cancels, right? So I have, this is the first equation. They tell us another 10 joules is needed to stretch from 12 centimeters to 14 centimeters of the natural length. So the second equation, the work is integral from 0.12 minus L to 0.14 minus L kx dx. This is equals to 10. So what they do after that is stretch that a bit further until the length is 14 centimeters, which is 0.14 meter. Okay? Now, of course, then the change is just 0.14 minus L, right? That's the terminal length beyond the natural length. So, just like before, this is k over 2x squared from 0.12 minus L, 0.14 minus L equals to 10. If I write the 10 on the left hand side, 10 equals to k over 2 times 0.14 minus L squared minus 0.12 minus L squared. Okay, so 20 equals to k times, actually I think it may be easier if you do difference of squares here, but this is 0.0196 minus 0.28 L plus L squared, that's for the first group, minus the second group 0.0144 minus 0.24 L plus L squared. We get 20 equals to k times this guy minus this guy, that's 52, 0.05, 0.0052, and then this guy combined with this, that's 0.04 L, and the L squared cancel. Right? Okay, so that's our equation 2. Let's put them together first. So the first equation is 0.0044k minus 0.04k L equals to 12. 0.0052k minus 0.04k L equals to 20. So if I subtract this, I get negative 0.0008k equals to negative 8. So my k is negative 8 over negative 0.0008. Let me move the decimal point 4 times to the right. So this becomes, this is equivalent to 8 with 4 zeros divided by 8. So k equals to 10,000. Now using that k, then I can find the L, which is the natural length. Okay? Which is the natural length. So which one do I want to use? Maybe I use equation 2. 20 equals to 10,000 times 0. Why do I do that? I can just distribute that. Oh, and then, you know what? I write it down first. 10,000 times 0.0052 minus 0.04 L. So multiply 1, 2, 3, 4. So this 52 minus 1, 2, 400 L. So 400 L equals to 32. L equals to 32 over 400. Reduced by 4, that will be 8 over 100 meters, which means this is 8 centimeters. Okay, that's the natural length. Maybe I describe that here. Let L be the natural length. I think this question is a bit more complicated. Yeah, the type of question we have maybe like number 10. Basically, you need to find the coefficient of the spring constant, okay, or spring coefficient. In other textbook they call that, right? And then use that spring coefficient function. Use that spring coefficient to generate the force function, okay, to compute the work in other case. Number 15. A cable that weighs 2 pounds per foot is used to lift 800 pounds of coal up a mine shaft of 500-meter deep. So let's say we have a mine shaft that is 500 feet deep. And then the coal down there is 800 pounds. Okay. You want to see how much work is done. You need to think this way. You need to think this way. Suppose the cable is now only X feet down. This is X feet down. So what is the force function? Okay, what is the weight of this cable? Cable weight. Yeah, let me use another color. So for this one here, the cable weight will be 2 times X, right? Because X feet times 2 pounds per foot, that's 2X. The total weight is 2X plus 800. Okay, now then the amount of work to be done will be, notice that your X starts from 500 becomes 0, or if we go backward, that's integral from 0 to 500 of 2X plus 800 dx. Is it okay? So that's the total weight, right? Multiplied by the infinitely small distance to travel, but you integrate by from 0 to 500. Okay, because the X originally 500 and eventually the X becomes 0. The amount of work, you can think of that, well, you go backward from 0 to 500. Okay, so this is X squared plus 800X from 0 to 500. This will be 25 with 4 zeros plus 800 times 500. What will that be? This is 250,000 plus 400,000. That's 650,000 foot-pounds. That's a lot of work, huh? Now, suppose I change the question later on that you pull the coal, not the whole 500 feet, but only you pull from 500 feet deep to, let's say, only 100 feet deep. So you stop at x equals to 100, for example, then the integral will be from 100 to 500. Okay, if that's the case. By the way, I think our textbook may do it in a slightly longer way. Let me change, move a bit here. You know what? I don't think I want to do this. But our textbook may do it this way. So the way they think may be, okay, this is the building. And then this is the cable. Let's say this is X feet. And then the weight, 800 pounds. Okay, our textbook may think this way. The work done is equals to the work done by the cable plus the work done by the weight, which in this case the coal. Okay, now the work done by the cable will be integral from 0 to 500. The weight of the cable when it is x feet down is 2x. Right? So when you integrate this, you will get x squared from 0 to 500 plus, so that becomes 250,000. While the work done by the coal, that's actually 800 pounds traveling 500 feet. Constant weight, right? So that's how we get that 400,000 feet pounds. Okay, so the total work done is 250,000 plus 400,000. That's how we get that 650,000 feet pounds. Okay.